Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smartyurl.it/Jedi. My advice on how to pass actuarial exams is at smartyurl.it/pass. This video channel is at smartyurl.it/pass actuarial exams. Here's information about online seminars and study manuals for exams P, FM, IFM, and LTAM that I offer. I direct the actuarial program at Illinois State University. You can find information about it at smartyurl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smartyurl.it/help ISU actuary. Here's a problem for today for exam LTAM for a special 2-year term insurance policy on X years old. You are given death benefits payable at the end of the half year of death. The amount of the death benefit is $300,000 for the first half year and increases by $30,000 per year, per half year, thereafter. QX is 0.16, QX plus 1 is 0.23, I upper 2 is 0.18. Deaths are assumed to follow a constant force of mortality between integral ages, which means ages that are integer numbers. Z is the present value random variable for this insurance. Calculate the probability that Z is more than 277,000. And here's the solution. Note that the effective half-a-year interest rate is 9%. Also, under the constant force of mortality between integral ages assumption, if you write mu x for the constant force between ages x and x plus 1, and mu x plus 1 for the constant force between ages x plus 1 and x plus 2, then 0.5 qx is equal to 1 minus 0.5 px, and that's equal to 1 minus e to the minus 0.5 mu x, which is 1 minus px to the power 0.5. So 1 minus the square root of 1 minus 0.16, and for this problem, and that's approximately 0.083485. And 0.5 qx plus 0.5 is 1 minus 0.5 p x plus 0.5, and that's equal to 1 minus px to the 0.5, so it's the same number as before. And then 0.5 q x plus 1 is 1 minus 0.5 p x plus 1, so it's 1 minus e to the minus 0.5 mu x plus 1, and that's equal to 1 minus px plus 1 to the power 0.5, and that's 1 minus the square root of 1 minus 0.23, so it's 0.122504, and 0.5 qx plus 1 x plus 1.5, is the same as the quantity we just calculated. Based on the above, probabilities of the insured dying in each of the 4 half years are differed by 0 years 0.5 qx, which is 0.5 qx, it's approximately 0.083485. Differed by 0.5 years 0.5 qx is 0.5 px times 0.5 qx plus 0.5, so it's 0.916515 times 0.083485. That's approximately 0.036515. And we get the 0.5 px, of course, as 1 minus 0.5 qx. And then differed by 1 year 0.5 qx is 1 px times 0.5 qx plus 1, which is 1 minus 0.16 times 0.122504, so it's approximately 0.102903. And then differed by, so I had a typo there, my apologies, differed by 1.5 0.5 qx. I had a 1 there, but of course, clearly it's about the next half a year. And that's equal to 1 px of px times 0.5 px plus 1, which, by the way, is equal to 1 minus 0.5 qx plus 1, and that 0.5 qx plus 1 was 0.122504, so this is 1 minus that. That's why you see that 0.877496 there, times 0.5 qx plus 1.5. And that number we calculated in the previous calculation, so we plug them all in and we get approximately 0.090297. And the random present value of the death benefit, therefore, is as a random variable, written out as a random variable, is equal to 300,000 divided by 1.09 for the death within the first half a year, and that's approximately 275,229.36 with probability 0.5 qx, which was approximately 0.083485. 330,000 divided by 1.09 squared, that's for death in the second half of the first year. That's approximately 277,754 754.40, I'm sorry, with probability 0.5 deferred by 0.5 years, 0.5 qx, which we calculate to be approximately 0.076515. Then it's 360,000 divided by 1.09 cubed. That's approximately 277,986.05 with probability deferred by 1 year, 0.5 qx, which is approximately 0.102903. And then 390,000 divided by 0.09 to the fourth, which is approximately 276,285.83 with probability, and my apologies, I had to correct it, it's probably deferred by 1.5 years, 0.5 qx. I had a 1 there, it's corrected to 1.5, that's the way it should be. That's in reference to death in the second half of the second year. That's approximately 0.090297. Also, z is 0 otherwise. And what is the probability that z is more than 277,000? Well, that happens in the case when it's 277,754.40, and that's the probability of that, or 277,986.05 with this probability 0.102903. So it's the sum of 0.076515 plus 0.102903, and that's approximately 0.179418, which is answer D. Please remember, this is copyrighted material. The problem itself belongs to the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.